Hello everyone, my name is Rebecca and today I'll be talking about the what, how and where of lasers. We use lasers or laser devices in our everyday lives, whether you notice it or not. Not only that, but here in Ireland we are investing more and more into development and production of lasers, so it will be a very interesting field to be involved in the next couple of years. The type of laser we'll be discussing today is a semiconductor laser or a laser diode. Semiconductor lasers work in a very similar way to LED lights, where atoms of the material that make the LEDs become energized when energy or electricity is applied to them. After a while, the electrons lose this energy and then emit light. The main difference between a semiconductor laser and an LED is lasers emit a form of light where each wavelength is the same, instead of emitting a white light like an LED does. This coherence of wavelengths gives the laser a specific colour and gives it the beam effect we're all so used to seeing with lasers. This is why the word laser stands for light amplification by stimulated emission of radiation. Now, this light is brought about by the use of specific materials that will be discussed more in detail later. IPIC specialises in creating lasers from start to finish. As lasers and the parts of lasers are very sensitive, they are produced in clean rooms like this at the Tyndall National Institute and then assembled and tested on site in labs that look like this. There are 7 layers to the semiconductor laser, which include a substrate, a buffer, an N-contact layer for the power supply, the N-type cladding layer, an active layer, the P-type cladding layer, and the P-contact layer. Now, with these household items you see in front of me, I'm going to show you how semiconductor lasers are made. First, we will start with the base or the substrate layer. The substrate layer is the thickest layer on the laser, which are usually made from wafers, which are also used on microchips. When the substrate is created, a layer of buffer is placed on top of it. On top of the buffer will be the negative contact plate of the battery. This, along with the positive contact plate, supplies electricity to the system. The next part of production is called epitaxial growth, and this is when layers of atoms build one on top of another to create the N-type cladding layer, the active layer, and the P-type cladding layer. The N-type cladding and P-type cladding are used to prevent light from diverting away from the active layer when light is produced. It also helps in the production of light, but I will get onto that later. The active layer is where the actual light is produced, and it remains there until it shoots out at the end of the laser, creating the laser beam. As I said before, the main difference between a laser and an LED is the materials that are used to make them. The main materials used in P and N-type cladding is indium phosphide, and the material of the active layer is indium gallium arsenide phosphide. Epitaxial growth is brought about by a process called metal organic chemical vapor deposition, or MOCVD. MOCVD happens in 2 steps, which are island nucleation and layer by layer growth. Island nucleation is when atoms on a surface move around until they find another atom to bond to. This happens continuously at different locations along the surface, which leads to little islands being formed. The second part of MOCVD is layer by layer growth, which happens when the first layer of the surface is covered and the process starts again on the next level. The next step of the semiconductor laser production is fabrication. The first important factor of fabrication is the reflective ends or cleaved facets. The cleaved facets prevent light escaping prematurely from the ends of the laser. Many lasers have a naturally reflective end, but usually one end is made highly reflective to prevent any light from escaping from that side. The second important factor is the power supply or electricity. The laser will not work without the power supply because it provides the current that the electrons need to become energized to make light. The theory behind how a semiconductor laser works is explained within the N cladding, P cladding, and active layer. The material used to create the cladding has been combined or doped with another material before it was put into the laser, creating the positive and negative region of the same material. The positive region or the P cladding layer has holes, and the negative region or the N cladding has electrons. Once the battery is connected to the laser, the electrons and holes begin to move to the active region where they will combine. For the two to combine, the electrons have to lose energy to be on the same energy level as the holes. The energy that is lost is emitted in the form of photons or light. This light then bounces around the active layer. It cannot escape through the layers of cladding due to the refractive index of the cladding being lower than that of the active region. After a while, the light will escape through the holes left by the cleave facet at one end and create the laser beam. Lasers and laser-based devices are commonly used in our everyday lives. A few examples would be laser cutting, laser eye surgery, optical fibre communication, and barcode scanners. That's all from me on today's episode of What, How and Where of Lasers. Thank you for listening and goodbye.